Hi, Oleksandr.
Hey, Boxuan, how are you?
Doing well, doing well.
Yeah, great.
Do you want to give everyone like microphone and camera access, or you
Yeah,
want?
but I just wonder how to do it without like,
Oh,
just give
doing
me
it
a
one by
second.
one?
Yeah, let
I
me
don't know.
try to. Okay, I try to update the settings. Yeah, I think probably new people who join will have this access, but let me just change this settings for other people.
Sure, great, thank you.
Yeah. So, yep, probably let's start it. Hello, everyone, again. Yeah, I hope everyone have.
Should we start recording?
It is recorded
Oh,
actually.
sorry.
Yeah. So hope everyone have a great day, morning or evening, depending on the time zone. Um, so the plan first we'll have Boxuan who will present new feature in JanusGraph 1.0, the ability to use string vertex IDs. Then we'll have Natalia. She probably will join a little bit later. She will speak about some experimental features which are not part of JanusGraph main code base yet. Those are core graph traversals, cross graph traversals, and graph index inline properties. And at the end, I will talk about some batch query improvements we had in JanusGraph 1.0, and as well as SQL storage layer improvements. And again, I remind that this meeting is being recorded. So if you are not comfortable sharing any information publicly, like your like organization where you work, like your name, your title, or whatever, feel free not to share anything extra. Then we have a Q&A box and chat. Feel free to drop your questions there and we will try to answer them. And yeah, I think without further ado, I will hand over to Boxuan.
Hey, thanks, Alex, and thanks everyone for coming. We have 3 speakers today, and my session is probably the easiest one, so I'll try to keep it quick. Let me start by sharing my screen. Sorry, just 1 second. I have to. Sorry, I have to join 2 minutes afterwards. I have to reopen my Teams to grant access. Sorry for that. See you in one or 2 minutes.
Yeah, sure, no problem. Yeah.
Hey, folks, sorry about that. Let me share my screen now. All right. I suppose you guys can see my screen. Let me know if you can't.
Yeah, we can.
Cool. So I'm going to do a demo on custom string vertex ID. My name is Boxuan Li. I'm a part of JanusGraph technical steering committee. And the background is simple. Since 2018, there's a huge race on the community which requires a way to define the vertex IDs in string format. And before 1.0.0 release, JanusGraph supports custom vertex ID, but there are 2 major drawbacks. First is fixed, meaning that you have to decide whether you want to enable this feature during creation of your graph. Once you have created your graph, you cannot make any change. like if you create your graph using default settings, then you wouldn't be able to define a custom vertex ID during the entire lifecycle of the graph. And the second drawback is we used to only support numerical, specifically the long data type in Java. And a lot of users want to use string, especially like they want to use UUID, and it's been a long wanting feature. So starting from 1.0.0, we have this string type vertex ID support. You can see it from the official doc. We have a dedicated page explaining the usage and a few notes around this feature. And in a nutshell, it's very easy to start using it. In your configuration file, you just set 2 lines, graph.setVertexID equals true. That is saying we allow users to set up their custom vertex ID. And the second option is graph.allow custom VID types is true. At the moment, we only support string and numerical data types, but in the future, if there's a need, we can easily extend to other data types. Usually, string type is what you need, because if you need to use UUID, you can always convert the UUID to string before you create a vertex. I think it's worth mentioning that turning on this option doesn't necessarily mean you have to provide your customer vertex ID all the time. Let me rephrase. Setting this option to be true doesn't mean your existing graph will be changed or anything. If you have an old JanusGraph version, like let's say 0.6.4, if you already have vertices, and if you want to upgrade your vertex, if you want to upgrade your graph to the 1.0.0, you can just set this to true and start providing your own custom vertex IDs. We'll do a short demo then. And the usage is very simple as well. You just provide a custom ID. So I'm going to do 2 short demos. One thing is to start a new graph, which is probably the easiest way to start using this feature. I'm going to use a Gremlin shell. It's essentially a console that allows you to do all the graph-related operations. And I'm going to use an in-memory graph database for the demo purpose. You can see this is the code I'm going to use. I open a graph, in-memory graph. I have altered this properties file by adding the 2 configs I just mentioned. And then you can start creating a graph. You can give a custom like UUID, converting it to string, and then add the vertex, or you can just provide your own custom vertex ID. And after committing it, you will be able to query that vertex back. And you might be wondering, what's this for? So this is documented in our official doc. Make sure you read it carefully before you start using this feature. That's because due to historical reasons, we have a reserved character, dash. Dash character is reserved in JanusGraph. And that means in your custom vertex ID, you cannot use this character unless you set this environment variable or you set this system property to tell JanusGraph that you don't want to use dash as the reserved element, as a reserved character. Instead, you want to use something else. Say, if you use @, then you have to make sure that all the time you passing the system variable or environment variable all the time. And in your custom vertex ID, you cannot use this custom character anymore. If you forget to provide this system property or environmental variable, you may not be able to read the vertex back because JanusGraph doesn't recognize the custom delimiter here. So when I start the Gremlin shell, I'm going to add this Java options. Of course, if you don't need to use dash in your vertex ID, then you don't need to do anything. All right, so let's go to JanusGraph 1.0.0 release. Oh, sorry. Yeah, I just mentioned you need to start the Gremlin shell by providing this special system property. Also, now our gremlin console is up. I'm just gonna copy the code. So we open an in-memory graph database. You can see this log saying that it's loading the JanusGraph relation delimiter from your system property. And we say we want to override the default reserved character using the @ character. And now you can add a vertex using the dash. If you try to add a vertex using the reserved character, it will throw an error. Yeah, it says you're using the reserved character. And now, once you turn on this custom vertex ID option, you have to provide your custom vertex ID. If you just try to create a vertex without providing a vertex ID, it will show you an error. And now let's do some queries. So you can see the two vertices have been inserted to the graph database. And when you query, you can start using your string vertex ID. So this is a quick demo that shows you how to start a graph from scratch. And next, I'm going to do a second demo, which is probably more relevant to most of our audience, which is to upgrade an existing graph to 1.0.0. So before the talk, I created a graph using the 0.6.4 version using AWS key space. So I'm going to go to the 0.6 folder just to show you, to prove that the graph has been created. I have loaded the graph of the gods graph to that graph database to show you how we can migrate from an old version and upgrade to the new version. Bear with me, it's a little bit slow because my AWS instance is not in the same region as my personal laptop. So it's going to be a little bit slow. All right, so now we have connected to our remote instance on AWS. Let's see all the vertices. So we have loaded the graph of the gods example also as shown on the official JanusGraph documentation. So there are a couple of vertices. We can see if we want to query using the vertex ID, you can see the vertex. There's a small note here. Before 1.0.0 version, since we don't support string vertex ID, what happens if you use string vertex ID like this? You will still be able to find that vertex because we'll try to guess and cast your string vertex ID to the long type, so that we know you're actually asking for this vertex. This is never documented in the official doc, but in case you have discovered this by yourself and you have been leveraging it, you have to be careful because in the new version, we don't support it anymore. I'll show you in a second. So now we have see the existing graph using the old version. Ignore that stack trace. This is a bug remaining unfixed in the old version. And now let's just use the new binary to connect to the graph. When you have an existing graph, you cannot just add these configurations to your config file. JanusGraph will ignore them because they're global offline configurations. You have to update them using the management interface. The reason is simple. If something is global, it means all the distributed JanusGraph instances are using them. So you can't just open one graph using these configs and to let JanusGraph magically help resolve the conflicts. That just doesn't work. JanusGraph will keep using this old version that's widely used in the cluster. This principle holds even though you only have one graph instance. You still need to use this graph management interface to change a global configuration. And this configuration is global offline, meaning that it's not just global, it also means you have to close all the graph instances before you change that configuration. So now we don't have any open graph instances. We can just change it. Otherwise, you need to close other graph instances. And after updating a global offline option, your current graph instance will be closed. So we need to open the graph again to do any query or to add any vertex. So this time it's using the default relation delimiter. So if I try to add a vertex that contains a dash, it will throw an exception saying that you can't use it. Cool. So now we have added this new vertex. Let's see all the existing vertices. So you can see both the old vertices created using the old JanusGraph instance and then this new vertex. Let's say, and you will be able to query it, and also the existing vertex will be there. But as I just mentioned, if you try to use string vertex to query back the old vertex, it won't work because now we treat them differently. The numeric 8320 and the string 8320 are different vertices now. And I can even create a vertex using the string. It won't throw an exception because it doesn't think these two vertices are equivalent. Even though on Gremlin console, when we display the vertex, we don't add a code around it. You need to know they're actually different vertices. So this is just a corner case, but I do want you to know about that, especially if you have been leveraging that. So yeah, that's the end of my quick demo. Everything else is documented in the official website. Go and check it out if you haven't. And if anyone has any question, feel free to type in the chat room or interrupting now.
Yeah,
otherwise,
cool. Thanks a lot.
So
yeah, it's a great demo. Yeah, I just think I don't have any questions because I was reviewing that your work previously. Just wanted to add that we do have an open issue to support other data types other than string data types. So it's kind of in the background. We kind of may tackle it later. For example, if currently you store UUID as ASCII string, you would take 36 characters to store it. So it will take 36 bytes instead of 16 bytes. But we do have like a plan later to maybe add in this data types. Yeah. And I will
especially if you really want it, you should go to the GitHub issues page, create a new issue, or thumbs up to the existing issue. Yeah, thanks, Alex.
Yeah, I just dropped the issue, so if anyone is interested, so please follow it. Yeah.
I actually have a question. So if I switch to this new format for IDs, can I do a live migration of my JanusGraph? So for example, I already have some data using IDs along. Should I first update the code, postpone any interactions with JanusGraph, upgrade it, and then leverage this new feature, or it can be a live migration.
Oh, you mean when you migrate to the new version, should you finish migration first and then turning this option on?
Yeah.
Is that your question? It doesn't matter. You can just do them at the same time. So yeah, the data part is backward compatible, so it will still be able to read your old data, especially except that once you turn on this feature, in your code, you must make sure that you start providing new vertices. You should start providing vertex IDs.
I see.
So yeah, the safer approach will always be to you first finish the migration and then you turn on this option. I think that's a safer, in general, a safer way to upgrade. But I don't see any problem if you want to do them at the same time.
Okay, and how do you indicate that that's the vertex of the new type where, yeah, the ID might not be long, but a different data type, like internally? Like
sorry.
So basically, yeah, all the data is serialized, right? You try to deserialize it. How do we know that this array of bytes you should treat as long or as a string?
Right, that's a good question. Internally, we added a bit that is a flag to help us judge what data type it is, and this change is fully backward compatible, so it doesn't affect your existing data. We're leveraging an old reserved bit for this change.
Okay, cool. Thanks.
You're welcome. Yeah, if you're interested in its internal implementation, you can check out the PR related to that issue.
Yeah, I just wanted to add the cool stuff that this bit, leveraging this bit, will allow us to actually to support any other data types later. So, which is cool. Yeah. So
yeah. Sorry, not a bit, but a byte. Yes, if it's just a bit, then we can only support 2 types.
Yeah. So yeah, I don't know if anyone else has any questions. If not, I think we can hand over to Natalia. And yeah, if any questions come up, then we'll answer after her presentation. Yeah.
Okay.
Hi, Natalia.
Hi. Let me just turn on my camera. Yeah, so I have prepared some presentation. So just, yeah, I'm a software engineer. My name is Natalia. Very passionate about JanusGraph, really like this project, like the community. So in my company, we've been leveraging JanusGraph for some production use cases. And we've been focusing recently a lot on performance and scalability of JanusGraph. So today, yeah, I want to show some experimental features that unfortunately didn't have time to land in this new release, but they are still like, even for us, experimental. But yeah, I hope eventually they might land. But yeah, I'll be very happy to share what we're looking for and what we've done so far. So let me share my screen. Okay, can you view the presentation? Can you see my presentation, guys?
I don't see it.
Nope, I don't see it.
Nope.
For some reason, maybe.
Oh, hold on, maybe it's because
Yeah, try to click on share and then probably, I don't know what operation.
Now?
No.
Sorry.
No, that's fine. Yeah,
yeah,
are you using like Microsoft Teams application or like in a Chrome?
In a Chrome, yeah. Unfortunately, my application crashed and I was not able to join the meeting.
Yeah, I see.
For some reason.
Yeah, because I'm also using Chrome and usually it works. I don't know, but it could be related to the drivers. So
You cannot see it?
no, it's not even sharing anything. Like
when I was trying to share, it
maybe
says
maybe you
you
could,
have to grant the permission.
yeah,
I
if
don't know if you see any other similar things.
If it doesn't work, optionally, you could send me the presentation. I will open on my laptop, share it, and then you will just let me know when to click.
Can I also quite really quickly try to join with the application itself? Because I tested this morning, it worked, and then I had troubles to join through application. Just a second.
Sure, no problem.
No, I cannot. Ay.
Maybe just send
it to you.
Yeah, I'll try to open it.
Hello, guys.
Hey.
Yeah, I'm Vlad. Just maybe if we have like 2 minutes while we are dealing with technical nuances.
Sure.
I have a very brief question. I saw that you actually included Elasticsearch to the new version of JanusGraph. So the question is about actually data types and indexing. What I see in the Elasticsearch, and it's a very useful thing, we can configure dynamic indexing, like a dynamic schema for index. For example, if we have something with a prefix, let's say string, it can be indexed by default like a string, integer as integer, doubles, etc. But in JanusGraph, it looks like we need to predefine the keys, like mapping, just like manually. So is that possible to actually define these indexes, like types of data we apply to some keys dynamically, like in Elasticsearch?
The thing is that whenever JanusGraph doesn't know about your data type, it tries to guess it and create a schema for this data type. So if you, for example, used a string property, JanusGraph, and you didn't define a schema for this property, JanusGraph will say that it is string. And so
still you can say that, you can explicitly say that your data type is object in JanusGraph.
Yeah.
You can say it's just object.class. I just don't know if it will work out because I never tried. You can try like saying your data type is object.class and turn on that Elasticsearch dynamic indexing option and just see if it works. If it doesn't, you can create an issue and we'll see how we can proceed. I think technically it's possible.
So the object, you mean apply object data type to key?
Yeah.
That we, okay. All right, thank you. I'll try.
I tried to actually grant presenter permission to everybody on the call. So yeah, Natalia should have this permission, but yeah, I know. Okay, just received the presentation. Okay, I'll try to share it. Give me a moment.
Yeah, I think it's because my Google Chrome didn't have access for sharing, as you said.
Yeah. There is a problem, a little problem, because I use LibreOffice to open it.
Okay.
And it opens, but the format is definitely
I see. So
broken.
let me try. Sorry.
Maybe I could just upload it into Google presentation. Maybe it will work. I'll try.
Let me try. Also, I give access to Google Chrome, but I have to restart it. Give me like 5 minutes. Sorry about that.
No problem. Yeah. Yeah, and about just jumping on this data type thing. Again, if you don't specify a data type, your data type is just guessed. So I would recommend always specifying proper data type for all your properties. Otherwise, you are just relying on JanusGraph guessing the data type, and then it might guess wrongly. You might want it to use object, but it created a property like a string, and then you are stuck with the string property. So yeah, but yeah, as Boxuan said, you can definitely define object and store whatever you want. Yeah.
Thank you. And just in case, if we'll define object, does it mean it should be like JSON kind of object, or it can be like any value?
So yeah, Boxuan, if you want to jump on it, but basically you need to have a serialization for this object. So you need to provide a proper, give me a second, proper serializer. And Natalia, I'm giving you a make a presenter. I think.
Let's try again.
Yeah.
Okay, I think now it should work.
Yeah, so you just provide a proper serialization for your data type. You need to implement the serialization. You cannot use just like a random object which is not serializable anyhow.
Can you see it now?
Yeah, we see it.
Perfect. Okay. So yeah, let me start with the use case. So first thing that I would like to cover is the performance improvement that we made by so-called inlining properties into the index values. So imagine we have a use case where we have different vertices that represent a city. For example, it can be Chicago, Los Angeles, Toulouse, Lyon, and there is a country name associated with them. And our use case is that we want to fetch all cities by the given country name. So a natural approach would be to build up an index by country name, the property country name of the vertex, and it will group all the vertices that belong to this country. So now when we, using JanusGraph, leverage the search, we provide for this table the country name, and it fetches us the vertices that belong to this country based on their property. But actually, it will not fetch the vertex itself with all the properties. It will just fetch the vertex reference. It will be like a vertex ID of city Chicago, vertex ID of city Paris, etc. So there will be additional hop in like traversal of the data where you actually through the country name you fetch the vertices IDs, and then for each individual vertices IDs you're going to fetch the properties for this vertex. So the time complexity for this type of search would be of 1 to fetch the vertex IDs represented in country, and then will be of n to fetch all the properties for the given vertices. So in our use case, we wanted to try to optimize this search query. For example, in such cases where we don't want to actually fetch all the properties of the given vertex, but maybe we're just interested in one property, let's say city name. How this can be improved from OF1 to OF(n) to OF1 one operation. So we decided that we can leverage a concept that at least I saw a long time ago, maybe like 15 years ago, was introduced in Microsoft SQL storages. They introduced embedded properties into the index structure itself. So basically you have the index key that is indexed and the reference to the row of the data, and you also have some properties that you're interested that might be attached to this vertex. So that's we decided to implement with JanusGraph. So what we did, like if we look at the graph index table itself in JanusGraph, that's where all index keys are being stored. So the current structure of the table, I will talk about the Cassandra example because that's the use case that I was working on, but it will fit on all different storages. So a partition key is the index key. Let's say it's a country name. The clustering key will be the vertex ID, and the role value is also a vertex ID that belongs to this index. So what we started doing, we started embedding into the value of the row, not just the vertex ID, but so-called inlined properties. So now the graph index table looks like that. So you still have the index key representing the country name. The clustering key is the vertex ID of the JanusGraph. And the row now contains any arbitrary number of the properties you actually want to inline with your index. So now, if you want to answer the question, what are the city names for the given country name, you have a constant search time because you are getting with your index key all the subset, and you have the city name embedded into the index value itself. So we made it generic enough, and it can support any properties, not just like a scalar value properties, but like list or set values. And we extended the JanusGraph schema builder to be able to provide this so-called inline field edge. So we also modified the schema metadata itself. So index definition, by default, it has the index field edge that points to the property that builds the index key. And we introduced a new inline field edge that connects to the property that is going to be inlined into this index structure. So that makes it generic enough, and it can support any type of properties you want to embed into your index value. So definitely this comes with overhead during the write time, because now you have, if property changes, you have to update the index structure. But if you're more oriented like to boost your read performance, that gives a very big boost to your operations. So the code might look like that. So based on our example where we have the city vertex, which has the property, let's say ID, city name, and country name. Now we build the index city by country, and the key of this index would be the country name, and you can specify the inline property key that you want to introduce into the index. So this is pretty cool, and it can again support arbitrary number of properties. And now having this, like if we go back to the use case, you basically for this search you are going, you don't have to perform step 3 of fetching properties for each individual vertex to get what you want. So yeah, that's one operation that we did. Any questions about this one?
Yeah, that's pretty cool actually. Let me drop a link to one of the old issues. It's not what you did, but the idea I had previously that in Elasticsearch, you did it for composite indexes, as far as I understand. But
yes, yeah, we didn't mix.
Yeah, And I had like an idea for mixed indexes because it's easier. We already store we already can store a source of data for Elasticsearch, and well, if your index uses Elasticsearch, then all you can do right now, we are returning only vertex ID when we are searching using Elasticsearch, but it's pretty easy to return source of data and or actually specify what to return exactly, like what properties to return. And I think with Elasticsearch it's kind of slightly easier because you mentioned that if property changes, you need to update an index. So I think, and this should be done on JanusGraph side. So
Yes.
we're kind of responsible for doing this, but with Elasticsearch, we just give work to Elasticsearch and please update the source of data and reindex it. So I think just these two features could work together actually, which is
I think it's pretty cool for this type of use cases where you want to have some minimum scope of the properties you want to fetch from the vertex itself, and it's much easier to embed it into the index and just get it from there. Like we got a very nice boost. Like we have a very high search operations. We might search by hundreds of thousands of vertices, and we've seen a big performance improvement with this type of change.
That's awesome.
Yeah, so thanks. That's one thing. I also wanted to share another interesting feature that I did. I'll share my screen again. So same presentation. Can you see it?
Yep.
Is it okay? Cool. So we also was thinking, is there? So I know that JanusGraph has an ability to support multiple graphs within same JanusGraph like instance application running. But there is no actually a way to connect these subgraphs between themselves. There is no way to build a connection from one graph sitting in one storage to another graph sitting in another storage. And that's the use case that we've been looking for, because we would like to be able to scale horizontally our graph installations and be able to navigate between graphs seamlessly, regardless if the opposite vertex sits in the same storage or it sits in a different storage. So I came up with this idea of cross-graph references. So here, just an example, like going to cities and countries. Let's say that we have a list of countries sitting in one graph, which is physically might be located in storage 1, and cities is sitting in another JanusGraph instance, which is physically being stored in a completely different like file system or storage system. So we provided a way to be able to connect a real edge between this and provide JanusGraph functionality to be able to traverse this edge and direct the call to fetch the properties of the vertex to a graph where it's being stored. So if we take a look at the edge store table, again, I was leveraging Cassandra, and it's the use case that's most simplest for me to explain. So in edge store, we're basically storing all our vertices and all our edges and properties related to this vertex. So the partition key in Cassandra is the vertex ID itself, and the clustering key, it's, for example, the property ID, the edge ID, and then you have the values of it. So edges have been stored in this table as well. And if we zoom in into the edge itself, which is a clustering key, so it's being represented, the key value itself, it's serialized byte array. And it's representing a prefix, which is always some like a bit flags indicating it's the system property or system edge, if it's edge or property, and the relation type ID. Then you have the opposite vertex ID on the other side of the edge, and some additional edge information like properties, the relation ID, etc. So what we were thinking, what if we take this edge and into the value, we will add not just the vertex ID, but the graph name where this vertex ID sits in. So we modified the edge serialization code to be able to append the graph name of the opposite vertex to the edge storage itself. So now when you're reading your edge and you're seeing that it has not just the vertex ID of the other side, but the graph name, it knows immediately that this vertex does not belong to the storage system, it belongs to the graph with a given name. So in order to be backwards compatible, I have to make a little hack. I had to add a bit flag indicating that it's a new format and you should expect the graph name being appended. So I just added like a 0 value to that. Maybe there are better suggestions, but that's how like this experimental version is done. But again, basically in the edge itself, I encrypt the opposite vertex ID and the optional graph name where this vertex ID sits in. So now when I'm going to read this connection, for example, I have the vertex and I say, give me all cities for the given country, and I know that my city might be in a different storage system, my graph deserialization, what will it do? It will, instead of building a standard cached vertex, which is JanusGraph's like standard representation of the vertex, it will build a new data type called different graph vertex. And that is done to be able to protect yourself to avoid any operations like read or write within open transaction. So once you, for example, did you return a list of vertices and you see that some of them are of type different graph vertex, the transaction knows that it should create or open a new transaction for the given graph and attach this new transaction to the to this different graph vertex. And then you can operate on this vertex, update properties, create new relationships, etc. So the code with this new subtype and this new API might look like that. So imagine, yeah, you're opening transaction for your country graph, and you are listing all vertices within this country. So they're sitting in one storage system. Then you say for the given country vertex, I want to get a city vertex. And we know that it's being stored in a completely different system. So now when you get these edges for the city, you can see that if I try to modify the edge itself, it's going to throw an exception. It's just a unit test, but it's going to throw an exception, say that this edge is not readable within given transaction. It belongs actually to different graph. You have to open a new transaction. So what I'm doing here, I'm extracting the graph name from the edge itself. I'm opening a new transaction or getting an already open transaction for the given graph name. I'm attaching this transaction to this new edge and then I can update properties or read properties from this edge. And if I'm modifying anything, I actually have to now to commit 2 transactions. It's kind of a distributed transaction. So what I did, I also broke up the transaction process into 2 steps. One is not doing anything to the storage itself. It's just preparing the data to be written. So it's like a snapshot of the data that is going to be sent to the storage system, and then you can actually commit. Like breaking this into 2 steps gives me an ability to introduce some guarding rails in case, because it's a distributed transaction, if one transaction fails, I can replay another one, or I can replay the first one. Here I just, prepare, commit, and then commit, but ideally, you would want to put some try-catch or retry logic around distributed transactions. But this gives me an ability to store entities in completely different systems, be able to fetch the relationships between them and continue editing them regardless if they've been stored in different graphs. So, yeah.
That's pretty awesome. I think, it's pretty nice feature, and quite a few companies, I would say, might benefit from it. So It's pretty cool. And yeah, I like how you did append graph ID into the edge structure. So I think yeah, it's cool.
Yeah. It also sounds pretty. Excuse me. It sounds pretty cool to me. I just wanted to understand a little bit more about the background and the use case, because when people have different graphs, they do so because they want isolation. They don't want one graph to interact with the other graph. And if you do need interaction between graphs, they will just create a giant graph at the first place. So what's the motivation behind this for your use case, Natalia?
Yeah, so basically, yeah, there are two requirements that I wanted to satisfy with this new functionality. One is scalability. For example, if my original storage cannot handle any more vertices, I can append in different storage and have still seamless relationships between them, especially on the application level. It will be still represented as single graph. So that's one, horizontal scale. And second, it still provides me a kind of isolation and resilience. So for example, let's say I'm running lots of operations on my city graphs. I'm updating some properties that are not related to countries. For example, I don't know, append the population to that, I append users to that. So these all operations will live within one single storage. And if my city graph, sitting in storage system, different storage system goes down, I don't care. Like my operations for cities would be still running because as long as I don't have to update the country related information.
If I understand correctly, are your two different graphs stored in two different Cassandra clusters?
Yes. For this particular use case, yeah, that can be completely different cluster storage.
Gotcha. That's pretty cool. Yeah, that's pretty cool. Thank you.
And yeah, like the use case as well that we have that I think might be nice as well is, for example, if you're using an API like GraphQL, this attaching of different transactions might be done on a GraphQL level, and from API perspective, you still get this like graph stitching seamless to the user, and it does seem like a single monolith graph to you, regardless of where it's being stored.
Yeah, makes sense. Thank you.
Yep, thank you so much. Anyone has any other questions?
Yeah, hi, my name is Jan. So yeah, basically, I think we already do something similar with upper layer. So basically querying over multiple graph databases with GraphQL. So that could be interesting. What I also thought of, we have a multi-tenant database. So each tenant has their own database with the same schema. So basically what could be interesting to save the schema in a different graph database to update the schema for all clients at the same time. That could be also.
Yeah, there are definitely some operations where you have to basically do a union of graphs. Yeah, like if you want to have a unified index, or you want to fetch, for example, a data is distributed among graphs. Like yeah, for multi-tenant stacks, it's very common use case where you want to unify all tenants. There definitely you have to be aware of all the possible graphs that you have, and you have to query each one of them and unify the data. But on the other hand, it gives you more possibility to distribute this request among different storages. Instead of hammering one single storage to pull out the big chunk of data, you can do it in parallel between different storages and then unify the data on application level. Any other questions?
Okay, I think if there are any other questions, You can again ask them in the chat or Q&A or after the presentations. I'll just cover some basic improvements on batch query processing and SQL. Give me a second, I will share my screen.
And if you have any follow-up questions, you can always feel free to ask in GitHub, in Stack Overflow, in our mailing list, or on Discord, our Discord channel.
Yeah. Do you see the presentation?
Yeah.
Yeah, perfect. So yeah, my name is Oleksandr Porunov, but you can call me Alex. I'm a principal software engineer at MAPT and JanusGraph Technical Steering Committee. And I will talk about batch queries and SQL improvements in JanusGraph 1.0. So basically, I decided to touch these separate topics in the same presentation, just because some of the batch queries features were driven by SQL improvements in the first place. So the first 7 slides will be related to batch query improvements, and the rest of them will be related to SQL improvements. So before we dive into the batch query improvements, I want to clarify what I mean when I talk about execution steps or parent steps. So execution steps referred in this presentation mean any steps which require fetching data from the storage backend itself. And parent step are those which pass their traversal to the children steps. So yeah. So the first feature which landed for parent steps improvements was removing unused JanusGraph multi-query step. So if you don't know, JanusGraph multi-query step is basically a wrapper around barrier step, which registers your vertices with any step which supports batch query optimization, or we call it multi-query. And so barrier step forces to process a specific number of traversals which come into the barrier step before starting processing the next step after the barrier step. And traverser is basically a wrapper around objects which is propagated through the traversal. And so traversal also has some metadata like current loop, that's history, and any other metadata. So previously, JanusGraph multi-query step would be placed before each execution step, which supports batch query optimization, as well as before each parent step, which is compatible with batch query optimization. However, in case the parent step doesn't contain any execution step which benefit from batch optimization, this would only cause some overhead to the query execution without actually providing any benefit. And by overhead, what I mean, imagine if the next step needs just a single element to be retrieved, we would still fetch many more elements in memory before proceeding to the next step, right? So by default, barrier step, which is inserted by multi-query optimization, is 2500. It is configured. It is configured. Can be configured use JanusGraph configurations, or if it is placed by lazy barrier optimization strategy, which is a tinker-pop optimization, it cannot be configured. It just hard-coded to 2500 right now. And so in JanusGraph 1.0, this behavior is fixed by removing any unused JanusGraph multi-query steps by the end of the optimization's lifecycle. And so the next feature was just adding support to all the parent steps, except match step and 3 use cases I will talk after that. And generally, we improved repeat step, how much optimizations are working in the repeat step. So basically, if we take a look on the diagram, we can see that repeat step has 2 common sources of data. So the first one, this one, the first source of data is from repeat step start traverser, and the second one is from repeat iteration itself. And this is going to be 2 sources of data for the repeat step. So previously, some of the use cases wouldn't register elements for batch processing for the next iteration, which would lead to smaller batch queries. And emit and until steps may sometimes have some children steps, which could also benefit from batch optimization, because emit and until step can, like in these examples, can have some other steps. Yeah, but however, previously they wouldn't receive any elements for batch registration, which could also lead to much smaller batches. And in JanusGraph 1.0, again, this was fixed, and all these steps can benefit from proper batch registration for each loop. Now, Tinkerpop's repeat step works in a breadth-first search mode. Moreover, emit or until steps will not be executed until all traversals of the current loop are executed. Only when a repeat step processes all the incoming traversals, the emit or until steps can be executed. And that's why we are able to properly register elements for batch queries for emit and until steps. However, as I said, there are 3 use cases I found which behave differently. And in these 3 use cases, until or emit steps are executed after each repeat iteration and not after each loop. So after each repeat iteration of the traversal. In such case, emit or until step, which come on the right side of the repeat step, will receive smaller chunks of data for batch query registration. But all other use cases with repeat steps, like having emit or a single emit or single until step, or having both emit and until steps on the right or on the left side, works as expected, basically. So I got some feedback that it has my previous description about multi-nested repeat steps was slightly confusing. So I'll try to cover it again. Feel free to drop any questions. So by multi-nested repeat steps, I mean this situation when we have a parent repeat step, and the parent repeat step has a children step, which is repeat step itself. And if we take a look, we see that parent repeat step has 2 sources of data. The first source of data is this input, which comes from the previous step. This is a traversal, which comes to the parent step. And the next source of data, as we talked before, is the next parent iteration. So these are two sources of data for normal parent repeat step. But if we talk about children repeat step, we see actually three sources of data. The first source of data is just the same as the parent repeat step source of data. First, we get a traversal which comes before parent repeat step, before the which comes from the previous step of the parent step. Then we get data which comes for the next iteration of the parent step, and we get also data from internal loop of the child repeat step itself. So it is three sources of data. The thing is that we not always want to receive vertices for batch processing from outer parent repeat steps. So let's take a look at this example. So we have V1, V2, and V3 vertices, which will be wrapped into separate traversals when they come into the parent repeat step. Meaning that in foo, this in step will execute a query separately for V1, V2, and V3 instead of executing them in a single batch. And this is the default behavior, which ensures no unnecessary data is fetched and no data is fetched multiple times due to small transaction cache. However, if you have big enough transaction cache to hold all your data during the parent repeat step and children repeat steps iterations, you might sometimes benefit from this mode we have, all repeat parents mode, which is configured by this property. In such case, the repeat step, the children repeat step will get a source of data from all the possible sources, basically. From all the three sources, it will get data from parents traversal, from parents next iteration traversal, and from internal repeat step traversal itself. And in some situations, we actually want to preserve the default behavioral, which is closest repeat parent behavior, where we registering data only for the children start, a repeat step start and repeat step next iterations. But we also want to register all the traversals from the parent start, from the parent repeat step start as well. For example, in this situation, if we use closest repeat parent mode, as I said, V1, V2, V3 will be executed separately. But if we use starts only of all repeat parents, we still preserve behavioral of the closest repeat parent, but for the first query, we will actually register all these three vertices together in a single batch transaction, in the single batch query. So first, I want to say that these are not production performance tests, but local tests which I run on my laptop with the local single node Cassandra for cluster, just single node Cassandra. All the benchmark tests presented here are available in JanusGraph repository, and you are free to execute them in your own cluster And in fact, all the parents are presented here optimized similarly, but have different performance characteristics just because different use cases traverse different amount of data and different amount of steps which benefit from batch query optimization. So here we see that repeat step usage patterns perform more than 10 times better because those patterns basically traverse the whole test data we have in JanusGraph and have two steps benefiting from the batch query. Like if we take a look, we have this and this steps which benefiting from batch query, or here even, oh, sorry, this one, no. This is for indices, so ignore has step. But in this situation, emit, for example, and repeat both benefiting from batch query optimization. Yeah, and all other use cases optimized nicely as well. And if you want to take a look at benchmark scores, you can follow this link. And yeah. Then, while we already had batch query optimization support for these steps marked in green, we did introduce new support for these steps marked in blue. And we also improved has step. So here I would like to talk about a first property configuration quickly, because it changed its meaning a little bit. Right now, it controls only direct properties fetching for vertices, meaning that it's not influencing Gremlin queries anymore. But if you have a vertex and executing properties method, then it may influence this execution. And in this situation, I just showcasing how it works. If you, by default, if you don't provide any properties, it will fetch all the properties for a vertex. If you enable this property, set it to true, and fetching just a single property, it will also fetch all the properties. And if you provide in multiple properties and set it to true, it will fetch only multiple properties, those properties which you provided in these situations, just two properties. Of course, if you disable this property, then the second example will return only a single property. Will fetch only a single property in memory instead of fetching all the properties. So what changed? This first property configuration doesn't influence the next Gremlin steps at all. But if you want to configure their behavioral, you can use this configuration, query batch properties mode. I said that this influences only direct vertices. It doesn't influence Gremlin steps, but it's not completely true. It does influence just a single, at this moment, just a single step. It is a has step. In case you enabled this property, set first property to true, then the whole this configuration will be overridden in all properties will be used instead, unless none mode is used. So yeah, I encourage you guys to take a look at query batch configuration namespace. Have more information on how how can you configure all the behavioral for different scenarios. So multi-query supports now multi-key and multi-slice features. The terminology may give some confusion to many JanusGraph users, thus we should probably improve the terminology, but right now it is what it is. So multi-query is a JanusGraph function, this one, JanusGraph function, which can be used to execute batch queries. In JanusGraph, when we talk about batch query or multi-query, we use this word interchangeably. It is the same, basically. Multi-query equals batch query in JanusGraph. We have slice query in JanusGraph, which is an internal query which we pass to a storage layer to be executed. The slice query returns different entries, usually property or edges, from slice start to slice end for a given partition key. The key is just the partition key is just encoded vertex ID. In JanusGraph 1.0, we introduced, I called it a hockey flag, direct called by start only allowed. Awful flag, I know, but while what does it mean? This flag basically means that this slice query is not a slice query. This slice query is direct equality query. That's it. Why we didn't change just the interface, because if we change the interface and produced not slice queries, but like direct equality queries, slice queries, then we would probably break a lot of JanusGraph adapters we have right now. So we probably should do this at some point, but probably like for JanusGraph 2.0 or something, I guess. But at least right now we can guess that slice queries can be executed as direct equality query instead of range operation, and it may benefit some storage implementations. Then we have multi-key. Multi-key just a feature which storage implementation may support or not. And this feature said that the storage implementation can execute a slice query for a set of keys. So basically you provide multiple vertices and you execute for multiple vertices, you may execute a single slice operation. And we have multi-slice feature. This feature is added in JanusGraph 1.0. And what it means basically that storage backend can execute, in addition to having multi-key support, it can execute multiple slice queries for a set of keys. So by default, all storage backends will have a default implementation, which is unoptimized implementation of this method, get multi-slices method. The default implementation is part of this interface, key column value store, and it's not optimized, meaning that each separate slice query will be executed using multi-key for a set of keys sequentially. But you are encouraged to override this method and implement your own optimized solution where you are executing multiple slice queries in parallel. And I just added a note that currently only SQL storage implementation has this support, but we can add support to HBase and other storage adapters. I think it shouldn't be a big problem. So again, as with previous benchmarks, these benchmarks are not production benchmarks, but instead they are tested locally. We can see that we improved performance for these steps more or less 10 times, depending on the use case. And you can follow these links to get more information about benchmark scores. So previously, CQL implementation didn't have multi-key support. Instead, typically for your operation, you would need to use a storage parallel backend ops thread pool, which did give some pressure on RAM as well as CPU due to thread context switching. And oftentimes, you might need to have thousands of threads to process heavy queries. This changed, and now we need only a single thread to process a single Gremlin query, while all other internal queries execution is handled using a synchronous approach. We see that depending on the use case, this improved performance from 34% and up to 100%. Moreover, SQL storage implementation become the first one which implemented my multi-slice support, as I said, and is now able to process multiple slice queries for a set of keys in parallel. And it gives us a performance boost from 24% improvement and up to 4.2 times better performance. Again, just local testing, not production, not production benchmarks. So we got slightly further with CQL improvements. As we saw earlier, slice queries now include this flag, direct column by start only allowed, which means that this slice query is actually not a slice, but a direct equality query. As such, storage backends don't need to execute range queries. They can optionally execute a direct equality query. And so in practice, this happens only when we want to fetch properties with cardinality single. However, I think that there might be some other use cases. So any slice query with these flags are now grouped together into a single SQL query, up to 20 slices per partition key. The limit can be increased using this configuration, default 20. Yeah, and with this improvement, we have seen performance improvement from 50% and up to 2.4 times better performance for different use cases. So we have a new feature also a new feature called SQL keys grouping. However, for most of the use cases, this feature isn't needed. So SQL keys grouping allows you to decrease the amount of executed SQL queries and expands to increasing the amount of bytes retrieved from the storage backend. So this is often useful if you are paying for each separate SQL query. Like, for example, if you are using AstroDB, they charge you for each executed SQL query. And by reducing the amount of queries, you may reduce your price. And in some situations, quite nicely, I would say. Notice that usually grouping by partition keys in a single SQL query is discouraged. However, JanusGraph has full view of the storage cluster as well as token ranges. And that's why it's able to group partition keys which belong either to the same replica set or to the same token range. So to not sacrifice performance, basically. Usually for ordinary Cassandra cluster as well as AstroDB, it works well. However, in case you are using ScyllaDB, you may, and you are using the driver which uses shard awareness optimization, then this feature don't have shard awareness grouping strategy yet. We did contact a ScyllaDB development team, and they said that they will improve their driver to provide publicly provide shard information inside. In that way, we can just add a new strategy, shard awareness with shard awareness, basically. We did have several more improvements. First, so storage SQL executor service, which was previously recommended to be disabled, now changed its meaning and is always enabled. For now on, this thread pool is used only for deserialization operations only and not for IO operations. And we do recommend to use the default value, which is nothing or -1. In such a case, it will use CPU count multiplied by 2, which is more or less the best for commodity hardware. Then we did introduce a ScyllaDB driver, which you can use, but currently you can use it either with embedded in embedded JanusGraph mode, or you can build distribution release yourself using this Malin command. So we did already have Cassandra for support, but in JanusGraph 1.0 we just improved testing, and we are testing against Cassandra 4. Boxuan improved Amazon managed key space support by allowing users to explicitly disable TTL, and Jan removed Cassandra all dependency, which was quite bulky. And we just copy paste some of the dependencies which are required for Hadoop into JanusGraph directly. So yeah, that's it. Here are just several useful links. The first one, if someone is interested to read more about batch queries improvements or SQL improvements, there are 2 links. Then I really recommend reading batch processing flow documentation if you are interested. And I think this one is must read for everyone link, which is upgrade instructions, because we did have a lot of breaking changes on the configuration level, not on the storage level, but on the configuration level. So, yep, thank you, everyone. If anyone has any questions, I'll happily answer them.
That's cool. I have a question. Do you guys have stats on what type of storages are being used, like the percentage-wise? What's the most popular and less popular?
We don't know, actually. The only thing I noticed that someone is adding a Couchbase storage backend right now in JanusGraph, which is an interesting thing, because they are adding the first probably storage backend, which is an index backend as well. So we'll see how it goes. Basically, they will use the storage backend and index backend, but it will be the same storage. I don't know, to be fair, how many people use that or that storage backend, but from my experience, mostly people use Cassandra, and slightly less people use HBase, but there are still many people use HBase. But there are also other adapters. Unfortunately, I didn't track like how many people use them, so not sure. But I guess we could reach to the developers of those adapters, like Foundation DB, and what else? There are several ones, and see if it is like used or not, if it is popular or not. For example, the DynamoDB. I know folks who are using right now the DynamoDB, but if you know that the DynamoDB storage adapter was archived and it's not publicly supported right now. However, I know folks who just, as far as I understand, forked it and improved it somehow, and they're using it at this moment with the latest JanusGraph. So that's all I have.
I see.
Yeah. A lot of questions we got regarding CQL. So I would assume it's Cassandra, but it's like, it's not based on any statistics.
Yeah, I would also guess so. I think the most popular one is CQL, but we do get many inquiries and questions around CQL. It doesn't necessarily mean it's the most popular one. Maybe it's just it's less easy to use, and people just in general have more questions. We just don't know. But yeah, based on our experience, we will say CQL is Cassandra is the most popular one.
Yeah. So yeah, I don't know if anyone has any other questions regarding the presented topics today, or maybe just generally about JanusGraph, like some JanusGraph features or something. Yeah, just let's wait for a couple of more minutes if we get some questions. Otherwise, I think it was quite a great session. And so do we have any GUI tool for JanusGraph to view the graphs? Yeah, there are quite a few visualization tools. And we do have links. If you go to JanusGraph repository, it lists all the supported GUIs. G.V, quite popular, and there are many other GUIs. So, are there any optimizations for supernodes in JanusGraph to process the query in parallel to return the results faster? Supernodes is an interesting topic. So JanusGraph has this this feature called partitioned vertex, right? But Boxuan can confirm that that feature is not supported, as far as I understand. Is not properly working.
It is available, but I personally don't recommend using it. It has some design flaws, and we know it still has some bugs.
Yeah, but what do you recommend about this to deal with a supernode problems? Would you recommend just to design users their own techniques of dealing with it and partition vertices by themselves?
My recommendation is to deal with this problem by user themselves. I see some other graph databases like Neo4j recommends a similar thing, that the ultimate way of solving it is to remodel your data to deal with supernode by yourself. We also had an open discussion on GitHub regarding this. Last year, I created a proof of concept. We had a discussion, but there wasn't too much interest in the community, so none of us continued on this topic. But if you have any idea, if you have anything, like if your use case, you believe that you cannot just remodel it from the user layer, you do require some sort of automatic way to solve the supernode problem, please comment in that discussion.
Yeah, perfect. Okay, I think it was a great session, and yeah, thank you everyone who attended, and yeah, we will post the recording to YouTube channel. Yeah, see you later. Thank you everyone.
Thank you.
Yeah,
Thank you.
bye-bye.
See you.
Thank you.
Bye.
Thank you.
Bye.